Hi, in this video we are going to calculate the Fourier series coefficients of the output signal of a linear time invariant system when the input signal is given as a periodic signal. Okay, first let us define the problem. Now we have a linear time invariant system with impulse response h of t given as follows, given as h of t is equal to 1 for t between 0 and small case t0 and 0 otherwise. Remember that the impulse response is the output signal when the input is a unit impulse. Now, the input signal x of t is given as now we have our well-known periodic impulse train, which is given by the following expression: m from minus infinity to plus infinity, delta of t minus m t 0. Now, so we have the fundamental period. This is a periodic signal with the fundamental period, capital T0. Okay, so the problem is calculate the output signal y of t. Now, remember our discussions in some other videos. In linear time invariant systems, if the input signal is a periodic signal, the output signal is also periodic with the same period. We have obtained this result, and computationally, we approach the problem in terms of the Fourier series representations. So therefore, we have to start with the calculation of the Fourier series representation of first the input signal. Now, x of t is periodic with fundamental period given by capital T0. So x of t has the Fourier series representation given as follows: k from minus infinity to plus infinity, h sub k e to jk omega 0 t, where omega 0 is related to the fundamental period by means of this expression. Okay, now ak can be calculated as 1 over t0 x of t multiplied by e to minus jk omega 0 t integrated with respect to t. Now we integrate over a period. And the simplest choice in this case is from minus t0 over 2 to t0 over 2. And in this interval, the signal x of t is delta of t. Sorry. Of course, we have the integral from minus t0 over 2 to t0 over 2, and then we have in that interval the signal is just delta of t e to minus jk omega 0 t integrated with respect to t. Now, by using the sampling property of the impulse, the integral becomes 1 because it just samples the value of e to minus jk omega 0 t at t equal to 0, where the impulse, the instant the impulse strikes, and the result is 1 over t0. So the input signal, the Fourier series representation of the input signal, is from minus infinity to plus infinity 1 over t0. All ak's are equal e to jk omega 0 t. Okay, now how can we proceed? Now we are going to continue as follows. We know that, sorry, this is of course plus jk omega 0 t. We have the Fourier series representation. We know that the complex exponential signal is an eigenfunction of linear time invariant systems, which means that it is essentially unchanged when it passes through the system, only multiplied by a complex constant. Okay, so we are going to make use of this fact, and then we are going to obtain the Fourier series representation of the output signal. Okay, so let us continue by first obtaining the output signal corresponding to the individual complex exponential signals forming the Fourier series. In the Fourier series, we have a superposition or a linear combination of these complex exponentials. So we are going to calculate the response corresponding to each complex exponential signal, and then we are going to obtain the Fourier series representation of y of t. So now let us look at this problem. Okay, now x of t is given as k from minus infinity to plus infinity 1 over t0 e to jk omega 0 t. Now let us calculate the output corresponding to each individual complex exponential signal. So we are going to do the following. We have this LTI system. The impulse response, remember, in the LTI system is very important because it carries all the information related to that system. And now our input is e to jk omega 0 t for an arbitrary k. So how do we calculate the output? Remember, the output is always e to jk, the input signal, e to jk omega 0 t, convolved with h of t. So the convolution of e to jk omega 0 t and h of t is the convolution integral, remember, is from minus infinity to plus infinity, e to jk omega 0 t minus tau h of tau integrated with respect to tau. Now, the term e to jk omega 0 t can be taken outside the integral, and the remaining integral is h of tau e to minus jk omega 0 tau integrated with respect to tau. Now, this clearly shows that the output is again the signal e to jk omega 0 t multiplied by this expression, but when we evaluate this integral, this turns out to be a complex constant. So the system action is just multiplication by a complex constant, because the complex exponential signal is an eigenfunction of any linear time invariant system. So, let us look at this integral separately from minus infinity to plus infinity. H of tau e to minus jk omega 0 tau integrated with respect to tau is, now h of tau is equal to 1 only over the interval from 0 to t0. Outside that interval, it is equal to 0. Therefore, we have this simple integral. Okay, let us continue here. This integral is simply e to minus jk omega 0 tau divided by minus jk omega 0 evaluated at 0 and t0. So we have e to minus jk omega 0 t0 minus, when you evaluate the complex exponential at 0, it becomes 1 divided by minus jk omega 0. Okay, let us continue here. Now, this expression, okay, to get rid of this minus sign, let us interchange these two terms. So, we have 1 minus e to minus jk omega 0 t0 divided by jk omega 0. Okay, now in order to, in fact, we have obtained the result. This is our complex constant because, as you see, omega 0, t0, these are constant terms. For any k, we obtain a constant which is a complex constant multiplying e to jk omega 0 t. Okay, this is the system action because the complex exponential function is an eigenfunction. But let us obtain a nice looking expression by means of the following operations. Okay, now this expression can be written as follows. We take the term e to minus jk omega 0 t0 over 2 as the common term divided by jk omega 0. Then write this expression as e to jk omega 0 t0 over 2 minus e to minus jk omega 0 t0 over 2. And we do the following. Now we have e2 minus jk omega 0 t0 over 2. And let us look at this expression inside the brackets. It is 2j sine k omega 0 t0 over 2 divided by jk omega 0. Now we have sine of something divided by, partly we have a similar expression here. We have k omega 0. So we can divide and multiply by t0 to obtain the same argument. But first we write down this expression as follows. In fact, as you see, we are trying to obtain the sinc function. E2 minus jk omega 0 t0 over 2. Then we have 2j sine k. Now instead of omega 0, we can write 2 pi over t0. t0 over 2 divided by jk. Okay, we can write 2 pi over t0 instead of omega 0. And then we just do the following trick: multiply and divide by t0. Now these 2's will cancel out here, and this 2 will cancel out with that 2. This j will cancel out with this j, and we have, let us write down t0 at the beginning. t0 e2 minus jk omega 0 t0 over 2. And we have sine k pi t0 over capital T0 divided by k pi T0 over capital T0. So we recognize this as the sinc function, in fact. So the result is T0 e2 minus jk omega 0 T0 over 2 sinc, okay, sinc function of k T0 over capital T0. Okay, so this is the system response. In fact, this constant multiplier is given by means of this expression. So by linearity, now when x of t is chosen as the individual complex exponential signal e to jk omega 0 t, we obtain e to jk omega 0 t multiplied by this constant. Okay, and therefore y of t will be the superposition of all these terms. So y of t will be equal to now for each individual component in x of t, the multiplier, the Fourier coefficient, is 1 over t0. So we also have that term. So we have t0 over capital T0 e2 minus jk omega 0 t0 over 2 and sinc k t0 over capital T0 multiplied by e to jk omega 0 t. So this expression, the multiplier, is the Fourier series coefficient of y of t. The corresponding Fourier series coefficient for any k, the corresponding Fourier series coefficient is obtained by multiplying the original Fourier series coefficient of x of t, which is 1 over t0, by the constant term we have obtained when we applied the complex exponential signal e to jk omega 0 t as the input signal of our LTI system. And by linearity, these individual terms will be superposed to obtain the output y of t, which obviously is also a periodic signal with this Fourier series expansion. And the fundamental period is the same as the fundamental period of the input signal x of t. Okay, thanks for watching.